Graphing other rational functions. So these are graphing rational functions that you can't put into the transformation form because you cannot do synthetic division. And so there's a couple of things we need to talk about first. So we know vertical asymptotes, that is nothing new. So a vertical asymptote is found when you are trying to set the denominator equal to 0, because you're not allowed to divide by 0. So any x value that makes the bottom 0 is not going to be able to be used. And so we find that by factoring both the top and the bottom, set any factor that's in the denominator equal to 0, and solve for x. But related to a vertical asymptote is something called a removable discontinuity. What a removable discontinuity is this is a hole in your graph. Basically, it's an x value that you're not allowed to use, but it's not a vertical asymptote. And how you create these holes in your graphs, these removable discontinuities, is you factor the numerator and the denominator, and then you see if there's any factors that cancel. So if you have the same factor top and bottom, that creates a removable discontinuity. Finally, for the horizontal asymptotes, there's a bunch of rules that we have. And so we didn't have these last time because I could find the horizontal asymptote just by looking at K, the up and the down transformation. So here we have 3 different rules. We call it bottom heavy, top heavy, and equal. And these talk about the degree. And so for bottom heavy, if the degree of the numerator is less than the degree of the denominator, that's a typo, denominator. So if the So if you have a smaller degree on top than you do on bottom, so if we look at this example, the degree on the top is 1 and the degree on the bottom is 2. So this one is larger. That means your horizontal asymptote is automatically y equals 0 every time. So if you have a bottom heavy rational function, your horizontal asymptote is y equals 0. You also can have the reverse. If you have a top heavy rational function, so the degree of the numerator is higher than the degree of the denominator. So in this case, this number is larger. That means there is no horizontal asymptote. So top heavies don't have a horizontal boundary. Now, if you have equal degrees, top and bottom are both exactly the same. So these two are the same degree on the numerator and the denominator. What you do is you take the ratio of the leading coefficients. So remember, leading coefficients is the coefficient of where you found the degree. So in this case, A and B. Divide those out, simplify, and this will be your horizontal asymptote. So let's go ahead and find each one of these things for our first example. So here's our first example. Find the vertical asymptotes, horizontal, removable discontinuities, and domain for this function. And then we're also going to sketch our graph. So the general steps is, first things first is we need to factor the top and the bottom. So that's our first step, factor the numerator. Problem is, well, our numerator is 3x minus 1. Well, I can't factor that any further. 3x and negative 1 do not have a GCF. I don't have difference of squares. There isn't a B, and C that I can do factoring by grouping. So this guy does not factor, and that's fine. Not everything's going to factor. So now let's try to factor the denominator. I'm going to do D-N-O-M, denominator. So 2x plus 1. And again, 2x plus 1 also does not factor. There's no GCF, there's no grouping, none of that. So I have a rational function that I can't factor anything. And so this is the factored form that I'm going to have to work with. I can't make that any simpler than it already is. So the first thing I usually look for after factoring, so step 2, is I'll look for those removable discontinuities, those RDs, removable discontinuities. So let's look at that definition again. So here's removable discontinuities, and we'll say RD. That's what we usually abbreviate with. We already factored. And so the way we find removable discontinuities is see if there's any factors that cancel, divide out of the top and the bottom. So if I look at my rational function, I have 3x minus 1 and 2x plus 1. Those are not the same factor, so I can't get rid of anything. And so since there are no factors that cancel, we don't have any removable discontinuities. There is none. So on RD, I'm going to put none. Then the third thing I look for after that, I start to look for vertical asymptotes. And for the future, we do vertical asymptotes as VA because mathematicians are lazy and don't want to write vertical asymptote. So let's see how we find a vertical asymptote. So remember, these are VA. Factor the numerator and denominator. We did that. Set anything in the denominator equal to 0. And remember, this is after you look for anything that cancels, because if it cancels, it's a removable discontinuity. But since we didn't have any of this, we have to go straight to this guy now. So let's see. In the denominator, we have 2x plus 1. So 2x plus 1 equaling 0. And we're going to solve this out for x. So I'm going to subtract 1, divide by 2, and we get x is equal to negative 1/2. So this is my vertical asymptote. And make sure you have x equals. Now, if we try to plug that back in, watch what happens. If we do negative 1/2 and I plug that in here, well, 2 times negative 1/2 is a negative 1, and negative 1 plus 1 makes 0, and we're not allowed to divide by 0, which is why this creates a vertical asymptote, because I can't have that value of x. It's going to make a 0 in the bottom, which is not okay. Fourth thing I look for after getting rid of all of my possible x's is I look for the horizontal asymptotes. And we always use HA for those. And that's where you look at the degree. So let's look at the degree of the top, the numerator. So the highest exponent I have is a 1. So the degree of the top is 1. And then we look at the degree of the bottom, the denominator, which is also 1. So 1 and 1, these are the same. So let's look at my rules at the top. So for horizontal asymptotes, if we have the same degree, we're going to divide out the leading coefficients. So that means we're going to take, so we'll say y will equal the lead coefficient, COEFF, over lead coefficient. So that means the leading coefficient of my numerator is a 3. Leading coefficient of my denominator is a 2. And I can't make 3/2 any simpler. So that means this is my horizontal asymptote at y equals 3 over 2. Now, finally, let's go find the Y-intercept. So I know I don't have it at the top, but you shouldn't need any rules for a Y-intercept because Y-intercepts are always the same thing, found where x is equal to 0 every single time. So we're going to plug in x equals 0 to this original equation and get a coordinate. So we have y equals 3 times 0 minus 1 over 2 times 0 plus 1. Well, 3 times 0 is 0, 2 times 0 is 0, 0 minus 1 is negative 1, 0 plus 1 is 1, and negative 1 divided by 1 is negative 1. So my y-intercept is at 0, negative 1. And that helps you graph the function. That's what that's for. So let's go ahead and make a sketch now that we have all of our little pieces. So the vertical asymptote was at x equals negative 1/2, so it's going to be right here somewhere. And excuse my lines, they're not very straight when I go up and down. The horizontal asymptote was at 3/2, so that's about 1.5, so that's about right here. And it's a sketch. And the y-intercept is at 0, negative 1. Now here's why you need that y-intercept. Because we have to decide, do I start here in the bottom left or do I start in the top right? Well, since I know this, I know that one of my branches has to be here because I have to go through that coordinate. So that means my other branch has to be diagonal from that original. That's why the y-intercept is helpful. And in this case, there were no removable discontinuities. We will get to how to graph that in the next example. Finally, let's do domain. So we have all the x's such that x is an element of the all real numbers, but x is not allowed to be equal to. So let's see, which x's do I not have? That's my vertical asymptote. So I am not allowed to be negative 1/2. I can be every other x except for negative 1/2. So for number 2, starting out, I would like you to try to factor the numerator and the denominator on your own because factoring both of those pieces is how we find everything else. So pause the video, factor the numerator and the denominator, and then unpause and we'll do some of this stuff together one more time. And here's your factored form. So the numerator needed the AC method. So 2 times -3 is -6. What multiplies to -6 but adds to a 1 is 3 and -2. The denominator just needs a greatest common factor taken out, and that would be 2x. So our factored form is 2x plus 3 times x minus 1 over 2x times 2x plus 3. And now we start looking for our pieces. So again, the first thing I always try to look for is removable discontinuities. And the reason those are first is because those come from canceling a common factor. And if I look, I have a common factor of 2x plus 3. So this right here creates that removable discontinuity. So we're going to take that factor that canceled, 2x plus 3, and we're going to set it equal to 0 and figure out what x I'm not allowed to have. So we're going to subtract 3 from both sides, solve a basic two-step equation. 2x equals -3, divide by 2. So x equals to -3 over 2 is a removable point that I'm not allowed to have. Now, it is a coordinate point. So technically, this does also have a y value that will be a hole in the graph. Finding the y value is more of pre-calculus. So we're going to leave this as just a hole at x equals -3 over 2. There is a y value that goes with it. We're just not going to quite go that far with this. Step 2, now that I know which factor canceled, let's take the rest of it, what else is left in the bottom, and set that equal to 0 to find the vertical asymptotes. So 2x is left in the denominator, so we're going to set that equal to 0 and figure out where the vertical asymptote is, which in this case is x equals 0. So there is actually 2 x values you're not allowed to contain. You cannot have -3 over 2, and you cannot have an x value of 0. Third, now that we got rid of all the x's we're not allowed to have, let's look at the y values we're not allowed to have. So the horizontal asymptotes. So again, this looks at degree. So the degree of the top, look at the original function. Degree is 2. Degree of the denominator, degree of the bottom, is also 2. So these are the same. So when your degrees are the same, you're going to take the leading coefficients and divide them. So we're going to divide 2 over 4. And 2 over 4 is 1/2. So your horizontal asymptote is 1/2. Y equals 1 over 2. Lastly, let's look at the y-intercept. So step 4, y-intercept. And again, that is when x is equal to 0. So if we try to plug it in, I would use this function here because that's simpler because we got rid of those two. So all we really have is x minus 1 on the top, so 0 minus 1, over 2x on the bottom, so 2 times 0. But here we run into an issue. This is -1 over 0, and I'm not allowed to divide by 0. So that means I don't have a y-intercept. Because if you notice, that's where the vertical asymptote is. You'll never hit the y-axis because that's the boundary line. So that means I need another point to help me graph. So let's get at least what we can on the grid so far. So I have a vertical asymptote at x equals 0. So right here on, there we go. Can't do a straight line up and down. A horizontal asymptote at 1/2. So about right here. Oops, that's too high. 1.5. I need it at 1/2. There we go. And we have this removable discontinuity that we will get to. So I couldn't do the y-intercept because that's my boundary. So I still need to decide, well, am I going to be at the bottom left and the top right, or am I going to be on the other end like a reflection? So let's just grab a random point. Let's just find a point to help us graph. So let's just choose, let's say x equals 1. And I chose x equals 1 because x equals 1 is right here. It's not on any of the boundary lines, and it's clearly in one of the quadrants. So let's find the y value at x equals 1. And again, I'm going to use the simpler version here without that removable discontinuity factor. So y equals, we have 1 minus 1 over 2 times 1. Well, 1 minus 1 is 0, and 2 times 1 is 2. Well, 0 divided by 2 is 0. So the coordinate is 1, 0. So it'll be right here. Now that I know that that's a point, I know that my graph has to be in this bottom left and in this top right. So the y-intercept is helpful to tell you where to graph. If you ever end up in a situation where you don't have a y-intercept because your vertical asymptote is on the y-axis, then just pick another point. You could have also picked -1 or -4. It really didn't matter which x value you chose. I just chose one that I knew was simplest, that wasn't 0. Now let's talk about this removable discontinuity. How do we graph that? Well, that is a hole in your graph, so it's going to be an open circle. So find -3.5 on the x, which is about 1.5. And here is where my graph should hit 1.5. That is your removable discontinuity. That's how you graph that. We just put a open circle around where that x value should be. Again, we don't really know the y value because we haven't figured it out. This is just a sketch, but there should be a hole right here at x equals -3/2. So you have to make sure you include that in your graph. Okay, let's look at number 3. So I want you to pause the video and again, start by factoring the numerator and the denominator and writing the factored form, and then unpause to make sure that is correct. And here's what you should have had for your factored form. So the first thing, so step 2, is the first thing we're going to look for is any removable discontinuities. So pause the video and try to find your removable discontinuities. So x minus 2 is the factor that cancels, so that creates the removable discontinuity. Set it equal to 0 and solve. So we have a hole in our graph at x equals 2. So the third thing we look for is the vertical asymptotes. So pause the video and try to find your vertical asymptotes. Okay, so for the vertical asymptotes, we take whatever's left in the denominator after canceling, and we set it equal to 0 and solve and get our vertical asymptote. Step 4, find your horizontal asymptotes. So pause the video and try to find the horizontal asymptotes. We find horizontal asymptotes by looking at the degree. So the numerator has a degree of 2, denominator has a degree of 2. That is the same. So we're going to take the ratio, the division of the leading coefficients, which are also both 1s. So 1 divided by 1 is equal to 1. And finally, step 5, help yourself graph by finding the y-intercept. Pause the video and try to find the y-intercept. And we have a y-intercept of 0, -5. You can use either function, but this is definitely simpler because we got rid of a factor altogether. All we had to do was 0 minus 10 over 0 plus 2. And finally, I want you to go ahead and graph it and try to write your domain. So sketch your graph, including the removable discontinuity, and try to write the domain of this function. Pause the video and try it out. And here's the sketch of the graph along with the domain. So we have our vertical asymptote, our horizontal asymptote, and then using our y-intercept, we have our graph should be in the bottom right and the top left. Now, the removable discontinuity will be right here at x equals 2. Now, for your domain, remember, there's actually 2 x values you're not allowed to have. You can't have the vertical asymptote, which is normal, but we are also not allowed to have the x value of 2. So both of these need to be excluded from the domain. So x cannot be equal to 2, and x cannot be equal to -2. So for example 4, I want you to pause the video and factor the numerator. I will help you factor the denominator. So pause the video and factor the numerator, and then unpause and we'll work through the denominator together. And here's what you should have had for the numerator, 3x plus 4 times 2x minus 1. So for the denominator, we have a cubic function here, and we have 4 terms. So we are already set up for factoring by grouping. So we're going to split this guy in half, right in the middle. And 3x to the third and 4x squared, I can take out an x squared from both of those. So we're left with 3x plus 4. And then on the back two, I can divide out a -4 from 12x and 16. We're going to have -4 times 12 divided by 4 is 3x, and then -4, 16 divided by -4 is a +4. And so we have 3x plus 4 times x squared minus 4. Now, we're not quite done factoring for this one because x squared minus 4 is difference of squares. So I can take this piece even further. So that piece will factor into x plus 2 and x minus 2 because of the rule for difference of squares. And then the 3x plus 4 will just tag along with us. So there's actually 3 factors in the denominator. And so now let's write our factored form. Factored form. So in the numerator, we've got, so y equals 3x plus 4 times 2x minus 1. And in the denominator, we have the 3 factors. We have 3x plus 4 as one of the factors. We have x plus 2 as a factor, and we have x minus 2 as a factor. So you're going to pause the video and find all the pieces that we've been doing all day. So the vertical asymptotes, removable discontinuities, horizontal asymptotes, Y-intercept, domain, graph, everything on your own for this one. So I want you to pause the video and try to find those 5 things and then unpause for the solution. And here's all the information you should have had for example number 4. This one's a little different because there's 2 vertical asymptotes. So removable discontinuities are found by canceling out the 3x plus 4, which leaves us with 2 factors still in the denominator. So for the vertical asymptotes, we have to set both of those factors equal to 0 and solve. So we have a vertical asymptote at 2 and at -2. So our y-intercept will help us. Well, we're not allowed to cross a vertical asymptote. You can cross a horizontal one. You just can't cross a vertical one. So the center portion will actually look like this. It comes up and comes back down. You don't cross horizontals very often, but it can happen. Verticals, though, you will never allow to cross a vertical asymptote no matter what. And so our left and right pieces, well, one's going to be here and one will be here. So you kind of have a couple options with rational functions. You can either have the normal where it's top left, bottom right, bottom left, top right, or you can have the weird with like 2 boundary lines and they will look something like this. If the U is at the bottom, your 2 L's are at the top. If your U is at the top, your 2 L's are at the bottom. Now let's write our domain. So we have the set of x's such that x is an element of the all real numbers, but x is not allowed to be. So let's think, where are all of my x's that I can't have? Well, I can't have 2, I can't have -2, and I also can't have -4/3, which I actually forgot to graph. So let's go ahead and do that. So my domain actually consists of excluding 3 values of x, 2, -2, and -4/3. Let's graph our removable discontinuity to make this sketch a little more accurate. So -4/3 is about -1.3. So -1.3 will lie right here somewhere. So there's that removable discontinuity.